Thank you, Ali, for the introduction. And as Ali said, my name is Theuwissen, and I'm representing over here my tiny little small company, which is called Harvest Imaging. I do have my roots in Belgium, and at the KU Leuven, where I studied, and I also got my PhD over there. But most of my work, industrial work, went to, that's what I did in the Netherlands with Philips Research Labs and with DALSA. And I spent also 1 day in a week during, I think, 22 years at the University of Delft, but that was only 1 day in a week, as I said. All right, that's enough about me. We are going to talk today about image sensors, a kind of a brief introduction into image sensors. And after a short introduction, I will continue with the 2D, two-dimensional CMOS image sensors. That's basically what you and I have in our mobile phones. I will show you how the pixel works. And I also will show you, if I find, yeah, that works also. And I will show you also one common used architecture for the ADC that is being used in image sensors, and that is based on the single slope architecture. You will see, and I will show you some images, you will see that image sensors are not perfect, absolutely not. And then we talk about much more than the few noise sources that were mentioned by Ali already. We talk about defect pixels, about defect columns, and so on and so forth. But finally, in the end image and the end result, we don't see all these defects. And that is done, the correction of these defects is being done by the ISP, the image signal processor. I will show you some ideas about that as well. And then we come, of course, to the conclusions. What are solid-state image sensors? And I always tell the people, try to explain that to your mother, what a solid-state image sensor is. And the more that you work in this field, the more difficult it becomes to explain that to a person who is not familiar at all with integrated circuit or with electronics. You can tell to your mother, for instance, that a solid-state image sensor is an integrated circuit. But then you take into account that she knows what an integrated circuit is, of course. But a bit more simpler and a bit also closer to the reality is that you can say, well, image sensors, solid-state image sensors, today they form the eyes of today's cameras. In the past, we had imaging tubes in a camera, but these days we don't see imaging tubes anymore. It's all solid-state, it's all ICs. And they are located directly behind the lens. So if you screw off the lens of a camera, then basically the first thing what you see is the solid-state image sensor. And why are they placed directly behind the lens? Because they have to convert the incoming information, and in this case that is light. They have to convert the incoming information into something that we can measure, something that we can manipulate, a signal that we can work on, process, so to say. Image sensors, they are very small in size and they are very light in weight. One of the smallest cameras even, so that's more than an image sensor, one of the smallest cameras shown over here, that is 1 millimeter by 1 millimeter by 1 millimeter, and that is being used for endoscopes. And in this particular case, this extremely small image sensor, or camera basically, is used for what we call a bronchoscope that goes inside, deep inside your lungs. The doctor wants to go with that endoscope in the smallest locations in your lungs, and that's the reason why it needs to be that small. They are produced on very sophisticated equipment that is basically not only for image sensors, that is for integrated circuits as such in general, and it's very, very difficult to produce them defect-free. In my early days, when I was much younger and we were working on CCDs at that time for cameras, we had to make them defect-free. Because at that time, the processing power and the memory, they were not available to correct all these details at the video speed, let's say, of 50 frames in a second. But these days, it's much easier. These days, it's much easier to correct the defects. And you can understand that if it's difficult to produce them defect-free, and if you use very sophisticated equipment, they are very expensive. But very expensive, or rather expensive as is shown over here, is also very relative. Keep in mind that the front side image sensor that is used at the front side camera of your mobile phone, that's what we call the selfie camera, that piece of silicon is being sold for 25 dollar cents, a quarter euro, a quarter of a dollar. And still people are complaining that it's too expensive. Only the sensor, only the die. So in the mobile world, they kill each other for every single dollar cent. It's incredible cost driven. And then finally, it's my own bread and butter. That's already, I don't know exactly, for over 40 years I'm already working on solid-state image sensors. Solid-state image sensors are used in applications where we would like to copy the use of the functionality of the human eye. You try to make copies of the things that we observe with the human eye, and then you think about a camcorder or digital photography. If you go on holiday, you take a picture of a beautiful landscape, and if you are back home, you would like to see the same thing on your monitor as what you have seen with your own eyes. But basically, in the same category, also a scanner does the same thing. A scanner is basically making a photograph, a picture of a piece of paper, for instance, and then you transmit it to the other side of the world. But there are a lot of applications out for solid-state image sensors that basically surpass the human visual system. And then you can think, for instance, about high-speed imaging. And these days we have on the market already cameras that make more than 100 million frames in a second, 100 million images in a second. We, with our human eyes, we do something like 7, 8 images in a second, but just for a very, very short period of time. But cameras, they go much higher. Metrology, we cannot do any absolute measurement with the human eye. And basically, that's the only thing that the camera does. It is measuring how many photons do come in a particular amount of time. We only do absolute measurements with our image sensors. Extended wavelength. The human eye is very limited, but silicon does. It's a much broader spectrum. It's covering a much broader spectrum. Operating conditions. We operate the human eye at 36, 37 degrees C. If you operate at 40 degrees C, you become sick. At 42 degrees C, we have to bring you to the hospital. But solid-state image sensors, they can work up to 200 degrees C, and even at liquid nitrogen. Think about space applications, small size, endoscope, and so on and so forth. That's what I mentioned already. Yeah? You can make a very nice analogy between, on one hand, a solid-state image sensor and the human visual system, in the same way as you make an analogy between a digital computer and the human brain. And there are a lot of things that we can do much, much faster with a digital computer compared to the human brain. But if you look to imaging, we still can learn from biology. For instance, the power consumption of the human visual system is extremely low compared to what we do in a mobile phone with our camera. We do a lot of processing on the retina level between the rods and the cones in the human eye to reduce the amount of data. That's still not done at a digital image sensor. So we still can improve, and there's still a long way to go, basically, to come to the same functionality in all aspects as what we have with the human eye. I show you here on the next sheet, I show you a floor plan of a solid-state image sensor. In this particular case, a CMOS image sensor. You see the central part are the pixels, the light-sensitive parts. But around these pixels, we have a lot of periphery circuits, analog, digital, and mixed signal. An awful lot of extra circuits are being added on the chip itself to actually correct the data, to synchronize, and all that kind of stuff. By the way, a silicon device is not sensitive to various colors, so we have to help the image sensor to detect color, and that is what I will show you immediately on the next sheet. But before continuing to the next sheet, I would like to tell you that pixels these days have a size of 0.5 micrometer. Can you imagine? 0.5 micrometer. Of course, you have them also larger, especially for industrial applications. But pixel numbers, they go up from 100,000, that is what we call a low number of pixels, a low amount of pixels, up to 500 million. Samsung announced for coming year, 2025, a mobile phone with 500 million pixels. What the hell can you do with 500 million pixels in your mobile phone? Chip size can go from 0.5 millimeter square up to 400 centimeter square. That's not a typo, centimeter square. That's a huge guy of 20 centimeter by 20 centimeter used in the medical world. So you have them in all varieties, but most of them are sensitive to color. But what I just said, electrons are not colored. Voltages are not colored. So you have to do something extra. And the something extra is being done by adding color filters on top of the pixels. So in the so-called Bayer pattern configuration, that is what you see over here, we cover every pixel with a color patch. So every pixel is becoming sensitive to red, green, or blue. And in this way, we detect the color. And then finally, you have a nice picture actually over here that shows you all the circuitry. I have to be careful over here. All the circuitry, left, right, top, bottom, around the image sensor. And of course, the central part over here are the pixels. Yeah? And how does this work? Well, this works very similar, or the architecture, the overall architecture is very similar to a digital memory. You see that we have a two-dimensional array over here of our pixels. The orange parts, the L-shaped parts over here are the photodiodes. And within the photodiodes, we have a small buffer to buffer the signal to the outside world. And we address all these photodiodes line by line, and then within one line, pixel after pixel. That is basically the same thing, of very similar to a digital memory. You see that all photodiodes on one line over here, on one row, on one line, they are being addressed by these transistors, and they are addressed at the same time. And then they bring the signals down on these, what we call column buses, what we just have seen in one of the sheets of Ali that was called the bit lines. But basically it's the same. Basically it's the same. We need an addressing circuit. That's very often, not to say always, digital circuitry, as you can see over here. Everything in yellow is digital, everything in green is analog circuitry, and then the photodiodes, as I just said to you. So we address them row-wise, row after row, but then within one row, you also need to address all the pixels one after another. And that is being done with an extra circuitry, extra horizontal shift register, or addressing circuitry to address the pixels one after another in one horizontal line. And then you bring the signal to the outside world. And in the early days of CMOS image sensors, the buffer over here, the buffer at the output, was an analog device. But that's old-fashioned. These days, we don't work with analog outputs. Well, there are a few exceptions. Canon, for instance. Canon is a very famous camera manufacturer. They use still analog output. But most of them, they have a digital output, an ADC, analog to digital converter. And Chris is going to tell us later much more about ADC configurations that you can use basically also in combination with an image sensor. But I will highlight one of them, and that is coming later, the so-called single slope ADC. But I would like to focus first on the pixels. So let's put a kind of magnification glass on top of the pixels. And then a pixel starts with a photodiode, of course. Of course. And one of my beloved questions to students is, what's the difference between a photodiode and a regular diode? Or the difference between a photodiode and a solar cell? It seems very straightforward because everything is a p-n junction. Because over here we are working with a photodiode, and the photodiode actually is used to convert incoming photons into an electron-hole pair. Actually, I have to admit that is not 100% correct, because it's the silicon that is converting the photons into an electron-hole pair. And the one who invented this, or actually the one who discovered this and described this, was already Albert Einstein, more than I had in mind to say 1 decade, more than 1 century ago. So it's the silicon that basically converts the incoming photon into an electron-hole pair, and then we do need a photodiode to separate the electron from the hole. And we store the electrons very nicely in the photodiode on the junction capacitance, and the holes are being drained to the substrate. We do not measure the instantaneously generated photon current because that can be extremely, extremely small with low lights. And that is becoming very hard to detect. So what we are going to do is we are going to integrate during what we call the exposure or integration time during 20 milliseconds, or maybe during 1 millisecond, or maybe during 1 hour, all depending on the application. We are integrating the signal on the photodiode. And after the exposure time, after the integration time, we bring that signal, we bring these electrons onto a capacitor. And basically what we do on the capacitor is very simple. The charge packet is converted into a voltage. And that is done by this very famous formula over here. I always tell my students, even if I do courses of 1 semester or something like that, if you would like to memorize one formula out of the whole course, that's the one that you need to memorize. And that's a very simple one. That's a very simple one. So you see that basically what you do is you bring your charge packet, the Q, over here on this capacitor, and you convert that charge packet into a voltage. And that voltage is going to be measured then and being sent out of the imaging array. And the measurement of that voltage is being done by a buffer, by an analog buffer. And that analog buffer is bringing basically over here the signal on the column bus for further readout. Yeah, that is the basic concept of our device. But how is this then implemented in circuitry? This is implemented in circuitry by means of MOS transistors. And you see basically that the transfer is being done by a transfer transistor. Hard to believe that you do the transfer by a transfer transistor. We do have here our conversion node. This is our in-buffer amplifier. And we do have over here an extra, this is the switch that is going to be the row select. Now, there's one thing that I have to add over here, that is after you have read the sensor, after you have read the pixel, you know the signal and you are going to process, you need to get rid of it and prepare your output stage for the next readout. And that is being done over here by the reset transistor, by the reset switch over here, you see? So you have 1, 2, 3 switches, just open or closed, and one analog buffer stage over here in the pixel together with the photodiode. But that is actually the heart of the pixel. If we now show the transistors over here, then indeed we have our transfer gate, we have our reset transistor, we have the row select, and over here the in-pixel buffer, the analog circuitry over here is nothing else than a source follower. This is the driver of the source follower, and the load of the source follower is over here on the column bus, you see? The combination of the two, one is on the column bus, one is in the pixel, that is going to be our buffer. And you see that we do have, that's not so difficult to count, 1, 2, 3, 4 transistors in our pixel together with one capacitor over here and the photodiode. That's it. That's it. Our pixels are extremely, that's actually what we would like to have. Huh? Our pixels are extremely sensitive to electrons, to capture electrons, because you would like to capture also a very low light level, close to darkness. You would like to catch these signals, you would like to catch these electrons, but unfortunately, as we just have heard in the talk of Ali, also noise is basically represented by electrons. And these electrons, they do not carry a flag, and they say, I'm noise generated, don't collect me. And the other one says, I'm photo generated, please collect me. That's not the way it works. Our pixels collect everything. And that is also what we do see over here, that our pixels suffer from noise. And for those of you familiar, the major issue is KTC noise of charging and discharging this capacitor, 1/f noise of the source follower, offset of the source follower, and actually to get rid of these noise sources, we have to refer again to the famous book of Willy Sanson. But Willy says in his book, never use a source follower. And that's the only thing we do. That's the only thing we do in our pixels. We only have source followers. Why do we have source followers in contradiction to the advice of Willy Sanson? Well, because the source follower contains only one transistor. If you would like to build a buffer, really in CMOS, for instance, you need more transistors, and you need also P-type transistors, and they consume a lot of space. And I just told you, our pixels, we make pixels of 0.5 micrometer, and we still would like to have them light sensitive, so there's not that much space left for transistors. And that's the reason why we only use one transistor, unfortunately, against the advice of Willy. Yeah. But the solution over here, and then especially refer to the KTC noise, and I'm going to use that later on, the solution over here is correlated double sampling. We are going to sample the pixel not once, but twice. Once without signal, and a second time with signal. And then you subtract the two from each other, and then you cancel out quite a bit of noise. Not everything, but you cancel out quite a bit of noise. Correlated double sampling. Keep in mind that is coming back later. An incredible amount of person hours, person days, person months are being spent on this particular pixel to develop this pixel. And you might say, well, wow, my God, you have only 4 transistors and 3 of them are digital. Well, it's a bit more complicated because in that tiny, tiny small pixels, you would like to have the best signal that is possible. And I show you here a cross-section of the photodiode, and the photodiode is a little bit more complicated than just having a PN junction. You see over here, it's a double PN junction back to back. And the common part over here is the N- region. N- refers to lowly doped region over here. And there's another condition, without going too much into detail. This guy over here, this N- region, needs to be fully depleted, otherwise it does not work. You see that on the photodiode, there's not a single connection. There's not a connection to bias the photodiode or to reset the photodiode itself. You clean the photodiode by taking all the charges out of it. And to do so, you need a fully depleted N- region. And that is not so easy. That is absolutely not so easy. And that is one of the reasons why there are being spent so incredible amount of person hours on R&D to optimize this guy further. That's really, really, to get all the data out, to get even the last electron out of the photodiode onto your conversion node, that is very, very, very difficult. And you have a very tiny, small process window. to fabricate this. So as soon as you deviate a tiny little bit of implantation dose, of implantation energy, or these kind of things, then the guy doesn't work anymore. It's extremely, extremely sensitive. But once you have it under control, you get gorgeous pictures out of it. But you see, 0.5 by 0.5, that's to the extreme, 0.5 by 0.5 micrometer, and that is what you have to put in those pixels. And that's, you can guess, that not that much space is left for your photodiode. And this is the one that is converting the incoming light into your signal. And for that reason, people invented a solution to that, and that is the so-called shared photodiode, or the shared pixel concept. And what we do over here is the following. We have now, as an example, 1, 2, 3, 4 photodiodes with their transfer gates, and they have a common, over here you see it's connected, they have a common conversion node over here where you convert your charge into a voltage, and that's being read by one readout circuitry. So your reset source follower row select is now being shared by 4 photodiodes. And you can go even a step further. You can go even to, let's say, 8 photodiodes sharing the readout circuitry. And this is a widely used concept these days, the sharing, especially in the case that you go to pixels smaller than 2 by 2 micrometer, that people are using this. Just before we had, and without sharing, we had 4 transistors for every pixel. Now, if you count now the transistors, we have 4 transfer gates, the reset, the source follow, and the row select. Now we have 7 transistors for 4 pixels. That actually means that we have this beautiful pixel concept now with 1.75 transistor per pixel, you see? And that is actually the technology that is being used widely in digital or in CMOS image sensors. What you and I have in our mobile phones. This is actually the concept. Yeah. Going back to the overall architecture, going back to the two-dimensional architecture of our CMOS device with the ADC at the output, as you can see, I'm going to show you a formula over here that is telling me what is the frame rate. How many frames can I generate? How many pictures can I generate with this guy in 1 second? And the frame rate is nothing else than 1 over the frame time. So what I do over here in my formula is I calculate TF, that's the frame time by means of this formula, and then 1 over the TF is the frame rate. How many frames can I generate in 1 second with this guy? And if we have an ADC over here at the output, I'm using the following parameters. That is that the conversion time of my ADC is 1 microsecond. So it takes 1 microsecond to convert an analog signal into a digital signal. But then once you have the digital information over here, the bits available, you need to get rid of these bits. You need to spit them out, so to say, take them off chip. That is given by the TO, the output time, that is 15 nanoseconds. This guy, in my example over here, we have 12 bits. The ADC has 12 bits output. And actually, I'm sending out the information with 12 bits in parallel. Yeah, so we have 12 output lines, and all these bits come off the chip very nicely in parallel. M is the number of pixels on a row, and N is the number of lines that we have, the number of rows that we have, and the ratio between the two is 1.5. Now, if I use this formula over here, then what you see is that I calculate over here the conversion time for every pixel. This is the number of pixels that I have. This is the output time, so to get rid of the data, to get rid of my bits. This is the total number of bits divided by the number of bits in parallel. And if you use this formula, then we get the following result for what we call a global ADC, one ADC on the chip. So every pixel, every information has to pass through the same ADC. And this is the curve. And you see on the horizontal axis the number of pixels, and on the vertical axis the frame rate, the amount of frames that you have in a second. Be cautious, this is a log-log scale, and this is a huge scale over here. Between 2 ticks over here, we have a factor of 100, by the way, in the horizontal axis also. But this is a relative slow process, because all your pixels have to pass through the same ADC. And if you have 10 by 10 pixels or 32 by 32 pixels, that is what we sometimes see in industrial applications, it's no big deal. If you have 100 pixels or something like that, that's no big deal. But if you have a few million pixels, then you run into a problem, because all these guys have to pass through the same ADC. And this ADC is slowing down the overall process. Moreover, this ADC is also locally heating up the sensor in this corner over here. and increased temperature, remember what we have seen in the first talk, increased temperatures is increased noise. And that's a problem, or that can be a problem. So for that reason, basically for two reasons, the speed and also the noise or the heat, people went to a new architecture, and that is to have an ADC on every column. And that's what we call, believe it or not, that's what we call a column level ADC. And in the column level ADC, I use the same formula over here, as you can see, the same formula over here, except this guy over here is divided by M, because now I have M of these ADCs nicely in parallel. And if we look now to the graph, then you see indeed that we increase the speed. Over here you see that we increase the speed compared to the global ADC. We increase the speed, but at a particular moment you see that the two lines are running in parallel again. And the reason for that is that at a particular moment in this region over here, it's no longer the ADC that is limiting the speed, but it's the effect of getting rid of all your bits to get rid of the digital information off chip that is limiting your speed. So you have to do something about that. And the something about that can be done, for instance, by pushing more bits out in parallel. So here I change now, you see, N part is 144. So now I push out 12 pixels, or the information of 12 pixels nicely in parallel. And then you see the result over here, that again you increase in speed, which is pretty normal, which is pretty straightforward. That again you increase its speed. Now I have to go back. Yeah, sorry about that. I have to go back, and that is much more difficult than I thought. Is there an engineer? Oh, I had in mind, is there an engineer in the room? So here you see that actually, again, the limitation is to get rid of all the data. And that is what we see with high-speed imaging. I told you earlier we have devices of 100 mega frames in a second. That's the issue with these devices with the high speed. You need to get rid of the data. And then what you see is that you can solve the problem by indeed adding a lot of these bit lines in parallel, but that's going to cost you an awful lot on bond pads, on pins on your package. And we see that for these high-speed applications, that the package is becoming much more expensive than your piece of silicon. So it's always a trade-off where basically, how can I get the best, economically wise also, how can I get the best solution? Yeah. There's one step further. I don't have a sheet for that. There's one step further. We had a global ADC. We do have a column level ADC, and you can guess what's going to be the next one. That's a pixel level ADC. That is, we started off about 20 years ago with having an ADC in every pixel. But that is going to add an awful lot of extra transistors in every pixel, of course. So that is what's not the right solution. So that did not show up in products. But these days, what is going to happen, and I need 2 hands for that, what is going to happen is that we go to stacked solutions, that we put multiple layers on silicon on top of each other. And the top layer is going to be the image sensor, and the bottom layer is a layer that only contains ADCs. One ADC for every pixel. And you get a connection between the 2 layers on pixel level, from the top layer to the second layer. That's what we call a stacked solution. And that is becoming very popular, very, very popular these days. So that's even one step further than this. All right, my single slope ADC. A single slope ADC is a very simple architecture to convert analog signals into digital signals. A very simple architecture, and the beauty is that you can use this very nicely in parallel. And this is the ideal, more or less the ideal solution for our column level ADC, because that's where we have a lot of ADCs nicely in parallel. And how does this work? Well, the working principle is relatively simple, but the whole world is becoming relatively simple if you know how it works. So you start off with a digital counter over here with n bits. And this guy is simply counting 1, 2, 3, and so on and so forth. And that signal over here, that digital signal over here, is fed into a DAC ramp, a digital to analog converter. You convert that count, that increasing count rate, you convert that into a slope, into an analog signal. And that slope over here, that analog signal, is fed into a comparator. And this is my analog signal that I would like to convert in the digital domain. So what you see, this is increasing, slowly increasing, and at the moment that the 2 signals are becoming equal to each other, then the comparator is flipping state. And the comparator tells to the RAM over here, to the RAM memory over here, hey, I see 2 signals at my input, and these two signals are equal to each other. And one of these two signals, the ramp, one of these two signals is represented by this digital code. So that basically means that this guy needs to be represented by the same digital code. Latch it, take it into the memory. And that is actually the working principle over here of our single slope ADC. And you see that here again. It's difficult for me over here. This is the ramp. You see, the ramp is nicely increasing, increasing, increasing. And when the ramp is equal to the analog signal that you would like to convert, then our our comparator over here is nicely flipping state, and then you take this digital signal into your RAM, into your memory, and that is how it works. You need, if you have multiple of these guys next to each other, you have an A to D converter on every column, then actually you need only one RAM generator. What you need on every column is basically a comparator, and that is being shown over here. You see here the two-dimensional array, the pixels over here. You need a comparator for every column, and you need a RAM and memory for every column. Yeah, and that is very nice because you only have one RAM generator over here, so you're very efficient in that. And that is nicely fed to all these RAMs nicely in parallel. There's one drawback, and that is that you always have to go from your lowest level of the ramp to the highest level of the ramp. Because if this guy, for instance, has a low level, then it flips very early in the ramp generation stage. But if this guy over here has a signal close to saturation, you always have to go with your ramp till the very end. That's maybe a drawback, so the speed. But nevertheless, it's widely used, the single slope algorithm, the single slope ADCs. It's widely used in imaging. There are a lot of sophistications on this concept. I would like to show you one, and that is that you do not work with ramps over here, but that you do work with counters. So instead of having a RAM cell over here, you work with counters, and they run in parallel with the digital counter that is generating the ramp over here. And these counters, they are up-down counters. And what you do is, remember that I told you earlier, we are applying correlated double sampling, so that you sample your pixel twice. One is without signal, and the other one is with signal. So what you do is you offer over here on these capacitors, first all the signals without, all the column signals without pixel signal, yeah, so that you create a kind of a reference. And at that moment, you do over here the conversion with a down counting stage. So your counters are counting down. And at the moment that your comparator over here flips state, you stop the counter. But you keep that signal, you keep that result still in the counter as a kind of a memory. But you stop the counting. And if you have done for all the pixels your reference voltage, if you have done this, then you bring the actual pixel voltage on the capacitors over here, and then you flip over here from down counting to up counting. And then you do the conversion again. And that automatically subtracts, because you did a down counting, that automatically subtracts the first measurement from the second measurement. And you do basically in your ADC, you do also a kind of you do the correlated double sampling. Moreover, if this guy over here is also suffering from an offset in one way or another, you also counteract that offset. So it's a very efficient way of doing that. And you see that you have a lot of sophistication on top of a relative simple concept. Yeah. Well, nobody is perfect. Nobody is perfect. Neither are our sensors. And what I've done over here is the following. I show you an example of an output signal of an image sensor. Remember that we have color filters on top of the image sensor, on top of the pixels, and that can be seen over here. You don't see the color filters, but if you look very carefully, you can see over here a kind of a grid structure. And that grid structure over here is due to that color filter that is on top of the image sensor. And the color filter was the so-called Bayer pattern. This guy over here of 2 by 2 pixels is repeated all over the place, left, right, top, bottom. Now this is an artificial image. So what I did is I added temporal noise. I added spatial noise. The difference between the two, temporal noise is what we just have heard previously. The noise of a resistor is, for instance, temporal noise. But you also have spatial noise, and that means noise that is changing from pixel to pixel. Pixels are analog devices, and they are not equal to each other. Maybe they are equal to each other to 99.99%, but there's still something that is left there. still something that is left, and that is what we call spatial noise. Leakage current, pixel defects, pixels that are completely defect. You see here the white pixels. If you look carefully, you see also some black pixels over here, pixel defects, and column defects. They are being added. So you need a lot of sophistication and a lot of processing that is taking place afterwards to get rid of all these defects. I'm not going into detail because that will take us the whole day, so to say, to explain you all these algorithms. But at the end of the road, if you look carefully, at the end of the road, what is happening is that you turn this, what we call a raw image, that you turn this raw image into a beautiful image that you would like to show to your customers. And what is being done over here is that, first of all, your color filters give you the color and gives you in every picture one color. And what you see over here is that in every picture we have the three colors, red, green, and blue available. That is what we call demosaicing. So you have to find all these information and all these pixels. Where are we? Correction is done for temporal noise. We correct it for temporal noise. We correct it for spatial noise. That's very easy. Correcting for spatial noise is easy. Correcting for temporal noise is pretty difficult. We correct it for the leakage current, for the defect pixel, and also for the column defects. Defect pixel correction, that's no big deal. You will be surprised to know how many pixels are being corrected in your mobile phone image sensor. Defect columns, but we consumer, with our consumer eyes, we even do not see if people are correcting defect columns. And at this particular moment, we are even that far that in the medical world, they were refusing for a long, long time correction of defect columns. But these days, even in the medical world, people accept defect columns and correct the defect columns. Yeah, so that took all place over here in the correction of this image. But you don't see any defect pixel anymore. Right? You don't see the effect of any defect column anymore. So that is basically what is happening today when memory is becoming cheap and processing power is so powerful these days in your mobile phones. Do you know that at the moment that you hit in the mobile phone, at the moment that you hit the red button, that the picture is being taken already? So you think, oh, that's a beautiful scene. I'm going to hit the red button, and then the picture is, no, the picture is already taken at the moment that you hit the red button. Because as soon as you switch on the camera, then the camera starts grabbing images. And it stores them in a memory, first in, first out. And basically, at the moment that you hit the red button, it retrieves the last eight images and simply average them to get rid of the noise or to reduce the temporal noise. All that kind of tricks are being applied in a mobile phone. But if you look then to an image sensor or if you look to a camera for machine vision, then you apply other tricks and so on and so forth. Yeah. All right. So what can be learned basically? Well, I hope that I could show you that an image sensor is much more than a simple combination of a photodiode and a transistor. I was working for a manager who, for a long time, he thought that it was just indeed the connection of a transistor and a photodiode because that's CMOS, and CMOS is solving all the problems. Well, there's a little bit more to that. Image sensor is really a complex mixture of device physics. That's what I showed you, for instance, with the pin photodiode or with that photodiode with that fully depleted N region. Semiconductor technology, you have to work very closely together with the manufacturer, with the fab. Analog circuitry, digital circuitry, as well as mixed signal circuitry. You have to keep in mind that the human eye, and that is basically where you work for, that is your customer, the human eye is an extremely, extremely strict judge. Doesn't matter if it's digital photography or automotive or computer vision, you name it. If once that the human being is looking to images, we see very, very easily, the human eye is very, very easily attracted to all kinds of defects. Exactly the thing that you do not want, yeah, but you cannot change it. The design of an image sensor is a team effort, especially if you look to all these disciplines over here, then you can immediately guess that it has to be a team effort on design level, but also on technology level. You have to work very, very closely together with the fab, because if the fab is changing an implantation, or if you would like to have an implantation change, very often it's between very, very narrow windows and the process technology. You have to work very closely together with the guys who deliver the digital signal processor to basically correct all these defects. And we have seen in the early days of digital imaging that basically everybody was using everybody's digital image processor, but now we see that company A is specifically working together with company B, and they are nicely cooperating, and basically the image signal processor is nicely tuned on what company A is doing and these kind of things. Yeah. To really get the best out of it. It's hard to believe, but if you compare what we have these days, the amount of photons, that we have these days on a pixel and on your mobile phone, if you compare that with 15 years ago, then the amount of data that we have on the pixel is 1.5% of the incoming photons that we have 15 years ago. But nevertheless, the image's quality is extremely, extremely increased compared to what we had 1 or 2 decades ago. And that is basically to all these combinations and all these close cooperations over here. Then the question is, what is the future going to bring? Well, there's still quite a bit of room to improve, that we have to use more efficiently the incoming information. A green pixel is sensitive to green, and you make it sensitive to green by the color filter. That actually means that you throw away, for the green pixel, you throw away the red information and you throw away the blue information. And that's a pity, because you throw away 2/3 of the incoming information for color imaging. So can we make more efficient use of the incoming information? And there's a lot of work going on in that particular direction. Higher dynamic range, and that is especially needed for an industrial vision and automotive application. Dynamic range basically means that in one image you see details in dark and you see details in highlights. And the classical example for automotive, for instance, is that if you drive with your car through a tunnel and you see these very dark walls of the tunnel, you would like to see the details in these walls. You do not want to hit the walls with your car. But in the meantime, if you come to the exit of the tunnel, then you see maybe a beautiful landscape, sunshine, and so on and so forth. And then the contrast, the dynamic range between the dark walls and that landscape outside can easily go up to 120 dBs. That's what we call dynamic range. There's still a lot of work to do in that direction. Still a lot of work to do. High frame rates for motion picture applications, slow-mo. I don't know whether you have seen the Olympic Games a couple of weeks ago in Paris. These extremely beautiful images of the horses jumping over the fences and that kind of things. And then in slow motion. Or during the cycling, if somebody hits the wall, they show you these beautiful slow motion images. That's what I'm referring to. So they capture the information in 6 to 10 times higher frame rate, and then they display it at a normal frame rate, and then you get these beautiful, beautiful slow motion pictures. There's still a lot of work to do. And that actually means, or we can reach all these goals basically by more sophistication in pixel design, more sophistication in analog and digital signal processing, and that actually means that more talented circuit designers are needed. Are needed? No, are urgently needed. The solid-state imaging world, the CMOS guys, the CMOS image sensors guys, they are screaming for people. They are unbelievable. Everywhere, people are looking, or the companies are looking for designers, analog designers, digital designers, mixed signal, you name it. So they need you. They need you, yeah. And that's basically the end of my story. Thank you.